Thanks, everyone, and I hope you've managed to get sufficiently caffeinated and sugared up on the 6th floor. We're going to finish early and leave some time for questions. We're kind of wearing a couple of hats here. One of us is obviously the brains of the operation, and the other one of us is everything else. But seriously, we have been involved in a number of kind of pan-UCL data science activities over the past couple of years. And also things like setting up the Alan Turing Institute, which is the UK's new National Centre for Data Science. And this meeting actually came for us through Twitter. We were very excited to see what Dan and others have been doing with British Museum and data science. So we're really excited about engaging. It's great to see some people that we already know, like Melissa, and we're looking forward to meeting some more folks. So Sofia is going to kick off with maybe about 15 or 20 minutes on kind of the national and international data science landscape. And then I'm going to talk a little bit about what we do in our spare time, which is sort of research into networks and kind of how that fits into a broader data science picture. So without further ado, take it away.
I'm just going to apologize for being the thing that stands between you and the first nice summer weather of the year. But then I realized it wasn't me standing between you and the summer weather, it was him. But it's all right. So I'm going to talk a little bit broadly about data science, a little bit about the landscape internationally, and some more recent challenges that I've become involved with. So just to put the context in place, what is this thing they call data science? So it's definitely an interdisciplinary field. It's people coming together across disciplines, trying to come up with processes and systems to extract information, often about very messy or heterogeneous data that were collected for a different purpose than you're trying to use it for now. It draws inspiration from many different technical fields, such as statistics and machine learning, but also systems in computer science, databases, and even applied mathematics. And often the subject of discovery is not just simple values like the height of a population. It treats text, images, unstructured data, rather than more traditional forms. So then, having said what is data science, one can relate this to big data, which is the other buzzword that has come up. Now, big data is very much a consequence of the fact that we're always getting recorded these days, especially in the UK. Data is collected automatically, often without a clear purpose. Much of it is human subjects data, so it's data relating to people. And often there is not a clear sampling paradigm. What do I mean by that? Well, an old-fashioned statistician, what I was trained to be, would try to design an experiment where there was a paradigm where I would set out and design an experiment to understand about a particular phenomenon. Here instead, we're often talking about found data or really fortuitously discovered or collected data, where it's more unclear whether you can answer the question you wish to answer. What's the problem with these sorts of lack of design that we encounter? Well, we've all seen these generic and more specific examples, like, for instance, the Twitter data that people were mining after Hurricane Sandy in the US, where if you looked at the actual information available from the Twitter data from Hurricane Sandy, you would have thought that the main focus of the location was not geographically where it was actually at, but rather where people had the most devices, which had electricity and battery and could tweet. Another example is the street bump example, where it was decided that it was a good idea to try to figure out where to repair roads by basically having an app on people's phones to discover where were the most problems with the road network. And of course what you really learned was where did people have the most smartphones, not actually where the greatest problems were. So the big challenges that come from big data and data science is really one of being truthful to the general population that you're sampling, and being able to generalize what you appear to see in your sample relative to the whole population, and having a good balance between being able to re-represent the structure you see in the data versus getting a stable understanding of what's going on. So if you collected just a little bit more data, your view or opinions about the data set wouldn't continuously be changing. And this can be quite hard. A sort of a generic example is precision medicine, where you're really trying to discover a lot of different characteristics with very small populations, because you really think that everyone is quite different. Another facet of big data and data science is that a lot of the techniques that people are using are coming from the paradigm of prediction. Okay, a lot of it was generated by people who are trying to figure out what are your movie preferences, what are your shopping choices, and all of these sorts of questions, rather than trying to understand what type of person are you. You're really asking, can I predict what you would like in the future? And these are two very different paradigms which have been really pervasive in both computer science and statistics in a long time frame. And the problem is, if you're trying to predict, you have a very specific goal of trying to understand what's the next observation going to be. Well, if you're trying to estimate, you're trying to understand why is the next observation going to be a certain way. And this paradigm really means that depending on what your particular problem that you're trying to solve is, the tools that come from a prediction framework or an estimation framework might be more appropriate and might be more susceptible to explanation or query or complaint. For instance, if you're getting a mortgage application denied, you might not want to be told that, oh, it has the best predictive performance across this large sum sample of the population. You might want to know it's because you live in that particular city zone or something like that. What's the paradigms and ingredients that have really made big data and data science take up over the last few years? Well, I shouldn't be using words like huge, given this is an academic audience, but the computational paradigm has really changed, and this is really what has made a lot of the recent innovations we've seen, for instance, in shopping analytics, possible. There's been a number of paradigm shifts. Depending on which data scientist you speak to, they will come up with a new V, but definitely volume. We're having larger volumes of data. It's coming at us faster, it has a higher velocity. Variety comes back to my discussion about precision medicine. We're trying to explain more types of people because we're having data about more typical types of people. Variability means that we might end up with single individuals that are way off what you see as the general population. Veracity, can you actually account for where the data came from and what's its provenance? Visualization is something we've been talking about for much of today. And also figuring out what's the value of the data, where you're collecting it. Because if you're using found data, there's still a cost to storing it and analyzing, even if your collection of it was rather sort of subconsciously motivated that there should be some value in this data. And as I was already saying, depending on your scientific inquiry or your problem at hand, the retail paradigm of just trying to predict rather than understand might be more or less appropriate. So this is a little bit of a topic that's really springing up, and you might say, what sort of relevance does it have to you at this setting? Well, I sort of said at the beginning, we all deal nowadays with human subjects data, i.e. it's data collected about people. And most of the data sets we're looking at were generated about people because we're wanting to understand about some aspect of human behavior. And one of the concerns that come out is as we generate more and more data that might seem fairly innocuous to us at the point of collection, actually it's really giving away more and more of our privacy. And something that comes up as a huge concern is that when we collect bigger sets of data, have more complex algorithms, how can we really justify why or how we're taking certain decisions, especially when it relates to people? One of the key concerns is that people want decisions to be fair, and that really corresponds to what does fair mean in this context. And this could be fairly mundane. So if you're on a retail site and you're getting different offers from other people, that could be fair or unfair, but it's not going to have a major impact on your lives. While if it's more serious decisions, it's going to have a bigger, much bigger impact on our lives. And finally, very much consent. And again, I think this is something that's going to come up as a bugbear in our lives, because a lot of the data that's collected for another purpose I think society's willingness to share that data and even do things that look fairly innocuous, as in improving, for instance, just the way we treat that data in aggregate, is not going to be something people buy into at the high level setting. And as you've known, there have been a lot of scandals relating to the selling of data, and the UK has a fairly well-defined notion of the fact that you can't own data as properties. So if this is sort of a major theme that's going in data science at the moment, there's been a number of reports on how to handle and store and treat data. Both the Government Office of Science as well as the previous White House, I couldn't possibly speak for the current White House, have had reports in this area. And the Royal Society and the British Academy is just about to announce the findings of a major investigation on how to govern data. And one of the big changes in this is that you really can't separate algorithms and data anymore, because the data life cycle is integrated with algorithms, and so some of the governance mechanisms you need to impose are definitely different from what has historically been the case. I was just part of a committee led by the Royal Society, which has reported out on machine learning and its potential for societal impact over the next 5 to 10 years. And there's also a major project in the Institute of Electrical Engineers on the ethical consideration of autonomous systems. And finally, in this setting, data, the new GDPR that's going to come into force in 2018 has really changed how we handle and treat data, because some of the penalties imposed with incorrect treatment are going to be quite severe and not as toothless as previous legislation. So overall, there is a considerable realization in society overall and in government interest of needing to use these new possible sources of information. On one hand, people have even asked the rather provocative questions of, do we really need official statistics anymore, given we have just ubiquitously sampled overall very large covering data sets? And one of the reasons why is that you have to understand a full population, or you end up exactly in the setting we spoke before of with Street Bump, where we just found out about the wealthy segment of the population who had the right electrical devices for you to be able to ubiquitously sense what they're going on. And another major theme that's going on in data science is really the notion of open data and data sharing. So there's been multiple government initiatives about this in the UK, and there's a lot of third-party interests, such as the Open Data Institute. So what's going on in the UK in this field? Well, there's been a number of institutes that have been set up which have an interest in this area. In particular, Patrick already mentioned the Alan Turing Institute. There's also the Leverhulme Center for the Future of Intelligence in Cambridge, which has just started operating. And there are various university groups, as well as a continuous slight drain, which I think academics in general view with both skepticism and enthusiasm, of people going over to the commercial sector, including companies such as DeepMind that came out of UCL, as well as Magic Pony, which is more recent, that came out of Imperial. And part of this is also a realization for some of the big players that some of the ways we handle data and think about these large, sort of over across the entire world population data sets need some extra thinking, is the partnership in AI, which has been set up between Google and Amazon and some of the very big players in this area. So I'm actually going to skip that. If you look internationally what's going on in this area, well, the US, of course, has new institutes and centers cloning or being formed by the hour. Perhaps particularly notable there is the Berkeley Institute, the eScience Institute in the University of Washington, as well as Columbia as being some of the first. Cornell Tech and the Michigan Data Science initiatives are all major investment, Michigan corresponding to $100 million. Canada has just seen last year the announcement of their first Research Excellence Fund for 213 million Canadian dollars. And the Europe angle is seeing a lot of investment in Ireland, Spain, Paris-Saclay in France, and the Berlin Big Data Center, which is in Germany. But naturally, of course, places like China have seen considerable investment, with a lot of data science majors coming out of Europe and the US going back to China to work there. So you can sort of see a rich tapestry of really developments across the world, with people who are getting the analytics to work in this area. Internationally, there's concerns about skill gaps, especially of skill drained into industry. And also there are fundamental questions about what should be taught. Some places are choosing to really focus most of their training on particular technical sub-areas, but for instance, Paris-Saclay has taken the point of view that you need to join data science up with an application area and then train data science for X. And I'm just going to kick off before handing off to Patrick. If you're interested, we have our third conference, which is coming at the end of June. We're having as a sub-workshop? A sub-meeting. We're having a particular focus with half a day on data sharing across the private and the public sector, which I should also mention. The abstract submissions has gone, but if anyone is interested in big data and wants to present something as a poster, I'm sure we could still squeeze something in. Okay, over to you.
Thank you. So, so let me just pick up on a few of those points and swap over the slides at the same time. I think in the context of digital heritage, there are some interesting things to think about here. Sofia mentioned things like Magic Pony. A lot of so Magic Pony is all about imaging, and a lot of the expertise that went into the formation of that company came out of medical imaging. There are big data challenges there, and also sort of consumer camera imaging and things like that. So there is a lot of potential application of this type of technology as it becomes more hardened and sort of more robust to applications in digital heritage. I once worked on a problem about 15 years ago where we were trying to take pictures of rubble fragments and reassemble the statue that they had come from, and that problem was impossibly hard to solve at the time. But we're getting closer to be able to sort of do things like that, or at least think about how we might do things like that. So I'm going to talk just a little bit, maybe more specifically, about things that that relate both to sort of our research interests here, and then also I want to make some more connections with digital heritage. And I should add, I mean, Chris and Chiara and I and others have talked a little bit about this already, but there's already a kind of very interesting nexus forming between UCL, the Knowledge Quarter, which includes things like the British Museum and particularly the British Library, as well as the Turing Institute, and I think there'll be a lot of interesting things to do going forward there. Sofia mentioned some work that we had done in India. That arose, again, out of a connection actually through the British Library and a look at some ancient manuscripts. And so big data, interesting big data challenges abound, and a lot of the big network data challenges that abound, I think, are likely to come up in the analysis of large corpora of texts and things like that. So there are many interesting sort of domain questions that we can finally ask and answer sort of on this basis. So I wanted to talk just a little bit in more detail about some of the core technical challenges that that we're thinking about in terms of data science and big data today. This slide is not exactly from me. It's from a sort of almost year-long scoping exercise that we took nationally and internationally when we set up the Alan Turing Institute. So Sofia led the exercise. I ended up leading a number of the workshops, but we solicited proposals from people to tell us what they thought was important in data science and to hold a workshop about it. We had something like 100 proposals come in. We peer-reviewed them all. We green-lighted about 36 workshops. And out of this, in the summer of 2015, came a kind of very natural clustering of kind of core technical challenges in different areas. So not all of these are going to be directly related to your interests, but in terms of understanding where the field is likely to go in the coming 1 to 3 to 5 to 10, it's probably worth having a little bit of awareness with these topics. So first of all, one thing people are very interested in right now that's becoming more and more possible is the idea of automating and propagating uncertainty quantification. So if you've ever done an exercise that yields error bars, you'll know what I mean when I talk about uncertainty quantification. And the problem, of course, is that if I do 4 or 5 things in a row by way of analysis, each of which yields error bars, then it's not always obvious how to combine the uncertainty quantification and propagate it along. There are starting to be some new techniques, some things like probabilistic programming, which you might have heard of, which are designed to make this a little bit easier and more robust. So that's something that we may see coming down the pipe in the next few years. Another one, and this really speaks to kind of performance issues, is around co-designing algorithms and architectures. So you probably know that most of what we use in our PCs or even in GPUs are basically designed to do lots and lots of matrix multiplications. And because that's basically what computer graphics, for example, is. You do an analysis of a scene, you kind of run the physics forward, and when you discretize the physics and implement it on a machine, you end up multiplying lots of matrices and tables of numbers. So it's pretty natural that our chipsets these days are optimized to do that. But if you're doing something different, like large-scale graph search or a different kind of big data application, it's not necessarily the case anymore that algorithms and architectures are necessarily working well together. So there's a big open question right now about what the kind of key data science algorithms, or even we would call them sort of core algorithmic primitives, are actually going to look like. It might not be sort of multiplying matrices together anymore. We already know how to do that, and but there's a lot of things that we don't know how to do nearly as quickly. For example, dealing with large graphs. Controlling computational and statistical trade-offs is another key area. If you have a problem that is too big to address, either because of the volume of the data or the amount of computation that's required, one potential avenue is to coarsen the problem or coarsen the solution. And what we don't have right now is a kind of full-scale knob that we can turn that goes between very precise, detailed solutions to large data set challenges and very kind of coarse grain, quick and dirty solutions. So that's there's a theory out there kind of waiting to be discovered. And don't worry about the jargon that I've put underneath there. It's not important for our purposes. But what is important to understand is that we should come to a time when you should be able to iteratively refine the solution set to a large-scale big data problem. So starting with a very, very coarse, rough cut, and then gradually kind of dialing up the precision and up the computation at the same time. There will be a long program on this next year, a year from now actually, at the Isaac Newton Institute in Cambridge, which is the UK's main mathematical sciences institute that kind of hosts 6 months visiting programs. So this is a topic of much interest in the mathematics community right now. Fusing multimodal data at scale, I think that probably has some pretty clear implications when we think about the kind of analysis that would come up in digital heritage applications. In other cases, and maybe even in these cases, it can come from things like sensor networks that are taking all kinds of different readings at different spatial locations and different time points, and bringing together structured data that might look like images with unstructured data that might look like text. We lack a good overarching theory of how to do that in general right now. We end up kind of designing bespoke solutions on a case-by-case basis. Harnessing distributed computation. I think for our purposes, that's kind of an enabling technology to be able to do larger scale analysis. So an example from another field would be astronomy, where a telescope called the Square Kilometer Array is being built and hosted at a number of different locations around the globe. It's going to pull down a huge amount of data, and even designing the architecture to make sense of that data is a non-trivial problem. So the physicists in charge have been given about a decade to do it. I thought that sounded like a lot of time. They tell me they're completely scared. So obviously, however large you make the problem, we can always arrive at a point where it's sort of exceeding our current capacity to manage. Machine learning, so I'll say geometry and topology of data. So moving past relatively simple types of data, very structured types of data like speech and images, to things that are more interesting. So one problem that we've worked on is how to understand a collection of different networks. So an example would be, suppose you're looking at relationships between writers over a certain period of time, and you end up with a network of writers who reference one another's work. Analyzing one of those networks is sort of fairly clear what to do, but what if you have a whole collection of these networks and you want to kind of make sense of them as kind of like a cloud of points? Well, it's not, if you have data in 3 dimensions, then a point cloud is a pretty obvious and intuitive phenomenon, but if you have a collection of some more complicated type of data, it's less clear what this means. In social data science, this is just an acknowledgement that much of the data that we generate and care about at the moment ultimately is by, of, and about people. And so there are, I think, strong opportunities for the social sciences to play a stronger role in this type of analysis. And then streaming data and anomaly detection. So that's all about dynamics and change points. The easiest examples that come to mind are things like cybersecurity or financial data. But it can also be used as, again, a kind of rough triaging technique. If you have vast volumes of data to page through, you may kind of choose to treat your data in a streaming manner and look for outliers or anomalies just to kind of take a first rough cut through very large data sets. And then the last one I'll talk just a little bit about before we open it up for questions and let everybody back out into Gordon Square, is understanding networks. So networks are interesting because, as I just said, they're a little bit more complicated than than the recording you get from a microphone or the image that you take with a digital camera. So the thing that I've been interested in for the past few years, and Sofia and I have done a lot of this work together, is to try to come up with some kind of coherent analytical framework for making sense of these types of data objects. So in classical statistical analysis, you measure, you take a set of measurements, and if a model for those measurements is a linear relationship, then you have all kinds of techniques available to fit a straight line that interpolates amongst your data points, right? And that's fairly clear. That goes back at least to the time of Gauss, who came up with the idea of a least squares minimization criterion to solve this. So you have optimal algorithms. Thanks to the invention of statistics as a discipline, we have something called the analysis of variance, which in this case explains both the trend that you see in the data and the variability that you see around the line. And on the back of this comes all kind of things about optimal decision theory and game theory and all kinds of other wonderful stuff that that makes everything work from the kind of sensors that enable smart cities, right through to the success of radar in the Second World War. So on the other hand, for networks, it's a lot less clear. Basically, even though this looks like a very simple problem, the network analog is so difficult that it yields none of these things at the moment. So what I've done here is I've kind of pictured a representation of a network where I've taken the nodes and I've listed them as rows and columns in a matrix. And then every time 2 nodes in the network are connected, I've colored the corresponding entry of the matrix blue. And if they're not connected, I've colored it white. So this is a matrix representation of a graph. And then what I've actually hidden in here is a clique. It's a set of 6 nodes that are all maximally connected, so all to one another. So 6 friends who are each friends with the other 5, for example. And even a question like, well, how do I find a clique hidden in a large network, doesn't have a straightforward answer. So we have very little in the way of optimal algorithms. We don't know how to assess how good our models are for these types of data sets. And so in turn, we don't know how to make optimal decisions. So in short, if you were to defend, either academically or in a court of law, a decision that was made based on the analysis of a network type of algorithm, you'd be a little bit hard pressed to give a robust defense. The field is very, very new. These types of data sets were not really appearing before about 10 or 15 years ago. And so we're just at the very beginning of building up our mathematical understanding of how to make sense of these types of data objects. So I'll give just a couple of examples and then bring it to a close, and we can talk through some questions. So here's one that is kind of natural if you think about it. A network can be diffuse and pretty random, or it can be tightly clustered. So for example, the reason that recommendation systems work on Amazon and Netflix and things like that is because our kind of categories of interests and products, they cluster rather nicely. Right? So Amazon gets recommendations for me by putting me in a cluster of other past customers and recommending based on things that people in this cluster have bought. So one really simple statistical question you can ask is, if you give me a network and a putative clustering, so for example, suppose you look at a network of word co-occurrences in, I don't know, Shakespeare's writings, for example, and suppose that you think that there should be clustering on the basis of something else, like the year in which the texts were written, or the physical location in which the composition was done, etc. You might like to test how clustered versus unclustered a network actually is. And surprisingly enough, there are lots of heuristics to do this, but until relatively recently, we didn't have any way to reduce this to like a kind of classic canonical statistical test. So what you'd want is something like what I've shown at the top, where, well, apologies for the cursor there, it's sort of in the way. You know, you take one measurement of the network, and if the measurement is near 0 in the middle of the bell curve, then that would correspond to a kind of randomish network. And if the measurement is relatively large out in the tails, you would have something that's very, very structured. So an example would be, if you look at studies of self-reported friendships of students in high school, which is basically sort of GCSE A-level, if you cluster the students' friendships at random, you get a pictorial representation of a network which looks pretty diffuse. But if you form the clusters according to the year in school of the students, then suddenly it all becomes much, much clearer. And of course that makes sense. If you do the same thing on gender, if you do the same thing on race in this data set, you'll see similar types of effects. So there's nothing really surprising about the result, which is that if you do this in the right way, you can use an ordinary Z-test to determine how clustered your network is. But the thing that's a little bit amazing is just that this was something that we weren't able to do until very, very recently. I'm going to skip this in the interest of time and just talk about one other thing, which is another very natural idea, which is how might I compare two networks, or more networks than two, potentially. And again, I'll take an example from computational linguistics. Suppose we're looking at two putative bodies of work and we're trying to decide whether they are similar or different. And suppose that the textual analysis method that we've chosen yields up a network representation. So the technical stuff is sort of less important here. But what I want to get at is the fact that it is possible to write a kind of generic mathematical description that allows you to sort of make the differences between different types of networks. So here I've taken a network where I've just wired the edges at random. And what I've done is I've gone through and I've completed lots of triangles in the network. So I've added lots more edges to close triangles. So a triangle would be an example to say that we know each other, Chiara and I also know Sofia, and then today the triangle got completed because you two were introduced to each other. So in social networks, it's a pretty common phenomenon that networks that we observe tend to have lots and lots of triangles, because if we know somebody in common, then eventually they're likely to meet one another. So what you see here in this representation with these, this is called a violin plot. It's kind of like a histogram turned sideways. a bunch of them plotted against each other. You see exactly what you'd hope for, which is a bump, a spike here in exactly one portion, and that corresponds exactly to the extra triangles. If you look at a metabolic network in the C. elegans worm, you see a certain type of structure. If you look at a power grid network, this is a physical network of power substations in North America, you see a very, very different structure. So this isn't telling you anything really about what the network means, but it's giving you a statistical way to assess whether two networks or two sets of networks or a given network and a given model are sort of consistent with each other, or whether they differ by quite a great degree. So I think I'm just going to sort of stop there and add some final thinking about this. If you're interested in this area in particular, what's happening right now is the mathematical foundations are really sort of being built, and what we're trying very hard to do is come up with algorithms that work with this mathematical structure and kind of yield provable properties. So ultimately, the ability to prove things about the performance of algorithms is what allows us to kind of stand up and robustly defend the conclusions that we draw on the basis of these algorithms, rather than sort of explaining that we did sort of 7 heuristics in a row and we're not too sure what happened in the middle, but we got an answer. So anyway, so at the end of the day, of course, what this is important for is to enable clear and defensible insights for decision making, just like with the rest of statistics, and ultimately to take, you know, scientific data or data from the digital humanities or data from health and medicine, and be able to come up with actionable conclusions on the basis of it. I will stop there, and I think either or both of us would be delighted to take questions before we go outside and enjoy the nice weather. So thank you very much.